Hey there, and welcome. Today we're going to go on a pretty wild ride, a journey to the very heart of matter itself. Yep, we're diving deep to explore the tiny, powerful, and kind of mysterious world of the atomic nucleus. Let's get into it. So, here's the game plan for our trip. We've got 5 main stops. We'll kick things off with the absolute basics, the building blocks of everything. Then, we'll uncover a discovery involving gold that totally changed science. After that, we'll meet the nuclear family living inside the atom, learn how to count them, and finally, we'll check out some unstable atomic twins.
All right, first stop on our journey. Before we can get to the heart of the atom, we gotta understand what an atom even is. So let's set the stage.
You know, it's kind of mind-bending, but literally everything, the device you're watching this on, the air you're breathing, it's all made of these teeny tiny things called atoms. Thinkers way back in ancient Greece, like Democritus, first dreamed up this idea, and then centuries later, scientists like John Dalton came along and showed that, yeah, these fundamental building blocks are very, very real. Okay, so we've got these atoms, but for ages, there was this massive question mark hanging over everything. So let's head to our next stop and see how that mystery got solved. I mean, seriously, what's in there? Were they just solid little specks, like microscopic marbles? Or was there something more complex going on inside? This one question, kicked off one of the most important experiments in the history of physics. And the way they figured it out, it was just brilliantly simple. A scientist named Ernest Rutherford basically set up a tiny particle shooting gallery. He aimed to beam a really small positively charged particles at a sheet of gold foil that was unbelievably thin. And then he just watched to see where they went. And this is where things get crazy. The results were not at all what anyone expected. If atoms were solid, everything should have bounced off, right? But nope. Most of the particles flew straight through the foil like it wasn't even there. But a few of them were deflected, and some even bounced almost straight back. It was completely shocking. So, this one experiment completely flipped our understanding of the atom on its head. It could only mean one thing. An atom is mostly empty space. But right in the middle, there had to be something super small, super dense, and positively charged that was knocking those particles back. Rutherford had found it. He called this tiny core the nucleus. Okay, so we found this tiny little core. Now let's crank up the magnification and see who's actually living inside. Time to meet the residents. So all the particles living inside the nucleus get this cool family name, nucleons. It's really just a handy catch-all term for anything you find in there. And this family basically has 2 main members you need to know about. And here they are, the proton and the neutron. The proton, as its name might suggest, has a positive charge. The neutron is neutral. It has no charge at all. Rutherford, our gold foil guy, gets credit for the proton, and his colleague, James Chadwick, discovered the neutron a bit later. Now, the proton is absolutely crucial. That positive charge is important, sure, but what's really the big deal is that the number of protons is like the atom's social security number. It's a unique ID. If an atom has 6 protons, it's carbon, period. If it has 8, it's oxygen. That number defines everything. And then you've got the neutron, the proton's neutral buddy. It weighs about the same as a proton, but it's got no charge. So what's its job? Well, all those positive protons in the nucleus should be repelling each other, right? The neutron acts like a kind of nuclear glue, helping to hold the whole nucleus together and keep it stable. All right, so we've met the residents, but how do scientists keep track of them all? Well, it turns out there's a secret code they use to know exactly how many protons and neutrons are in any nucleus. Let's crack it. It all boils down to 2 key numbers. First, you've got the atomic number, which we call Z. Super simple, it's just the number of protons. That's the atom's ID. Then you have the mass number, or A, and that's the total count of everything in the nucleus, protons plus neutrons. And to make things easy, scientists have a standard way of writing this down. You'll see the element's symbol, X, with the mass number A up top and the atomic number Z at the bottom. So let's break this down with a real-world example. Good old carbon. We see C for carbon. At the bottom, Z is 6. That's its ID, which tells us it has 6 protons. Up top, A is 12. That's the total number of particles. So how many neutrons? Easy, just subtract. 12 total particles minus 6 protons leaves us with 6 neutrons. See? It's the perfect little code. All right, for our last stop, we're going to get into something really fascinating. This is what happens when that nice, neat system has some variations. when atoms can have twins, and when some of those nuclei get a little shaky. And that brings us to this idea of isotopes. The best way to think about them is like atomic twins. They're both the same element, which means, and this is key, they have the exact same number of protons, but they have a different number of neutrons. They're family, but they're not identical.
Carbon is the absolute classic example. The most common kind you'll find is carbon-12. It's got 6 protons and 6 neutrons. But its more famous twin is carbon-14. It still has 6 protons. It has to, or it wouldn't be carbon, but it's packing 8 neutrons. Same element, just a different weight. That's an isotope.
Now that little difference in the number of neutrons can have a massive impact. A nucleus like carbon-12 is perfectly balanced, it's totally stable. But others, like carbon-14, with those extra neutrons, they're not so balanced. You can imagine them as being unstable, a little shaky, or wobbly. So, what does a wobbly nucleus do to fix itself? Well, to get stable, it has to get rid of that extra energy. And it does that by basically spitting out tiny particles and energy. We call that process radioactive decay. It's the nucleus's way of finally chilling out and finding a stable state. And that really brings us to the big takeaway here. We went from discovering this tiny, dense core inside an atom all the way to realizing that this core isn't always permanent. It can be unstable, it can change, and that just makes you wonder, if the very heart of matter itself can transform, what other powerful secrets is it hiding?